Welcome back, everyone. So this would be our third and final week in Game AI for Unity. So before we get started, you know the drill. Please scan this QR code to check for attendance. So has everyone done it? Yep. Okay. Thank you, NUS, for the 2FA. Okay, so to recap what we have done in the previous weeks. So during our first week of Game AI workshop, we did finite state machines. And then last week we did pathfinding with Unity's Nav Mesh. So I did a brief mention that we'll be going through behavior tree this week. So yeah, we can get started. So behavior trees, just as the name imply, it's a tree. So it's a hierarchical tree-like structure that controls decision making in game AI, and it's sort of an evolution from finite state machines to handle more complex behavior because you can make it do more things and it's not restricted to very limited amount of explicit state transmissions as you do in finite state machines. So the way how it is it looks something like this, and as you can see it is a tree, but it's not a binary tree. As you can see, you can put more than one child nodes for one of the nodes. So yeah, so we will get started with by analyzing this tree, and I'll go through some of the terminologies that you would need to know about behavior trees so that you can implement it your own. So we always start a tree with the root node, and this is usually denoted by a not symbol inside the square for a behavior tree. And whether or not it's inside a square is actually very important when you draw the graph, because there are several shapes for a single node, for different nodes, yeah. So the starting point of the tree and the traversal of the tree always goes from left to right. It's not as if a decision tree where you ask a yes/no question and it transitions from left to right, or left or right. But this always goes from left to right, and it will always go this way in all implementations of decision trees that you can find on the market right now, or of behavior trees on the market right now. Then we have this arrow in a square, which is a sequence node. This is what we call a composite node or a flow node. Basically, it controls the flow of execution in your behavior tree. And the behavior of this is that it will try to execute all child node until it finds that one failed, and then it will return back to the original. And it will return back to the root and then try to traverse the tree again. There's the selector node, which is the opposite of what a sequence node does. So it's also a composite of flow node. And what it does is that it executes all the child node until one of the nodes succeeds, and then it returns and then goes back to the higher level of this node to continue its execution. Then we have an action node, which is a square, and then you have behavior in it. It's a leaf node. You cannot add more behaviors to this anymore. You cannot add more child nodes to this. And then basically you attach a behavior to this action node, and then when it goes through this action node, it will execute this behavior logic. There's also the condition node, which is used to return a true or false. And it evaluates a given condition, and then it will return either true or false. In this case, true would be the successful message, and then false would be the failure message, usually. So, are we clear with the notations? Yeah. So now we can look back into what this graph actually does. So it all starts with the root node. I should turn on the laser pointer. It all starts with the root node, and then it traverses down where it reaches the sequence node. So the sequence node, similar to the root node, it will evaluate the left-hand side first. So it evaluates the left-hand side, and then it finds this. What is that called? The selector node. Yes. So it finds this selector node, and then evaluates the left-hand side, which it evaluates a condition. So the condition is if the objective position has been retrieved. If this returns false, then we will continue on with the execution. Because this is a selector node, it will keep on going until one of it succeeds. So it will go to this branch here, and then it will go into another selector node, which it branches into 3 different actions. It searches on the floor. If it can't find the object on the floor, then it goes on to this middle node where it searches in the drawers. If it still cannot find it in the drawers, then it will search in the closet. So in this process, if any one of these nodes will return true, it will traverse one level back to the graph, to this selector node, where it goes to the left-hand side again, and then it will say if objective position has been retrieved. Since we have already searched it, then it is pretty much true that objective position has been retrieved. So we'll traverse one level back again to this tree, and then we'll evaluate the right-hand side of this tree. So once again, we go through a selector node where it first checks the condition if the object has been grasped. If it hasn't, then it will go through this and then try to do a one-hand or a two-hand grasp, and one of these will succeed, and then it goes back up, and then it will check if object has been grasped. Yes, then it goes back up, and then since there's no more child nodes to be executed, and this is a sequence node, then this will just stop the execution of the behavior tree. Is that clear? I mean, it's quite straightforward. So yeah, we can summarize this as such. So it will first find the object. If the AI already knows the location of the object, it will skip the searching process. If not, it will search through those several predefined locations that we can find. Then it will grasp the object. If the AI is already grasping the object, then we do nothing. If not, it will try to either attempt a one-hand or a two-hand grasp, and then the state of this AI would end. It's as simple as that. So why do we choose behavior tree? You would probably ask, like, the finite state machine looks pretty powerful already. I can define like 20 states for the 20 different behaviors that I want my AI to do, and then just define very many transitions for it. The truth is, the finite state machines, even though they are very easy to set up and very straightforward to use, it's very difficult to scale. As you could imagine, if you want to make a complete graph with just 2 nodes, you only need 1 edge. But if you want to do it for 3 nodes, it goes to 3 edges, 4 nodes, and it expands quite exponentially. So as you increase the number of states, you have to define so many more transitions that it makes it very difficult for you to track. And it is not possible for you to make non-linear behavior. Non-linear behavior as in, certain behaviors would fail, and then it will try to do it again, or it will transition to a different behavior. As we have shown in the behavior graph that this is possible, in the behavior tree that this is possible. Obviously, there are cons to the behavior tree as well, right? The cons is that if you want to do a pure code-based approach, you don't want to use any sort of library that provides you with visual scripting or even some kind of code-based scripting approach for behavior trees, and you want to write the library from scratch yourself, it will give you a lot of headache because it's quite difficult to implement. Luckily for us, a lot of the game engines nowadays, including Unity and Unreal, has provided us with a very simple drag and drop approach for behavior trees that we can use to design, and it's very likely that you won't have to write a single line of code for easy AIs. And we'll look at how we can do that later. So, yeah. Any questions so far? No questions? No questions? Then we will go into the Unity behavior graph. So I'll explain what the Unity behavior graph is first. The Unity behavior graph is a visual scripting for behavior tree. So it's basically just drag and drop. It's like using Scratch. You have predefined blocks, and then you just need to define the transitions and the logic you want to do to go to each kind of different blocks. So it's much more visualizable because you can see what actions your AI is going to do. It's debuggable because on every stage of this behavior tree execution, you can debug it and then it will show you what step of execution it is in and what state of that execution it is in. And it comes with a lot of predefined out-of-the-box nodes, and I'll show you later what kind of nodes they provide you with. And then it also gives you the tooling that allows you to define your own custom nodes if in case one of your behaviors aren't available in the predefined out-of-the-box nodes that we want to use. Good. So that's the end of my slides. So it's coding time. So in this Unity project that we have left off last week, we have left off last week, yes. So what we're going to do here is first we need to install the behavior graph package, and you can do that in the package manager, and you just need to search the behavior and then it will show up. I've already installed it on my side, so you should install it on your side, and it's as simple as this. You just install this package and you immediately have support for behavior graphs. Okay, so once you have installed it, as you right click your context menu, in the create menu you would be able to see this behavior, this new context option called behavior that pops up, that you can create either a new blackboard or a new behavior graph. So specifically today we are only going to be looking at behavior graphs and just the very basic implementations and functions that you can do with behavior graph. And I think this would be enough to let you get started discovering what other more complex stuff you want to learn about behavior graphs in the future. So we're just going to go ahead and create one behavior graph in our enemy folder here. And I'm just going to call this the enemy behavior. So you'll notice that it creates a new asset, and it's okay if it has the same name as your scripts because it's not a C# script. It's just an asset. So as you double click on it, you will see this window, and this is your behavior graph inspector window. Here you'll see two things. The first one is the blackboard, and the second one is the inspector. And then you'll also see like this one node called onStart that is located in the middle of your behavior graph. So the inspector node is just similar to the inspector in your base Unity engine. It shows you the properties and the things that you can define and customize in any kind of nodes in this behavior graph. For this onStart node, you see that I can turn on either repeat or not. This will repeat the execution if the AI has finished, it has reached this end state. There's also blackboard, which serves as a collection of public variables that you want to expose to the rest of the game engine that your custom nodes and your editor instance will be able to access. If you don't define a variable here, you will not be able to change the values in the inspector, in the Unity editor inspector. And you will need to use this blackboard quite often. So we're just going to start very simple, and here in this window I'm just gonna right click and you can click on add, and it will pop this add node context menu for you. So what this add node context menu does is verbatim, it's just going to allow you to add new nodes, and you see there are several there are already several options available. We have actions, events, and flow. So the flows are the composite nodes, which I explained just now, is what you will be able to use for execution. For example, the sequence node is available here, and it doesn't have the symbols because it's much easier for you to read text. But we're not going to use this first. So there's also action, where you can see that it has very many predefined nodes for different categories that you can use. And we're just going to start off very easy. We're going to use the debug log message node. So this will log a message to the console, and then we will be able to change the log level here in the inspector. So for now, in the log, we're just going to type a very simple message called hello world. Okay, just to start off. And now that we have an action, we will need a way to transition to this action. So we need to define this connection here. From onStart, all you need to do is to point on it, and then you drag down to this node, and you will be able to get this arrow. You can drag this around, and you'll notice that it's not very nice looking if it's not like fully aligned. So luckily for us, Unity has provided this tool for us to align it immediately. You just need to right click on one of the nodes and click on align and select all children, and it will align the nodes immediately for you. Okay, very simple. So we're just going to attach this to our enemy AI. And here from the enemy behavior script, I just want to remove it immediately, entirely, because we don't need it anymore. We don't need some kind of script to control our AI's behavior anymore. We just need the behavior graph. So it's as simple as just dragging in this asset into your enemy game object, and it will immediately attach the behavior agent component onto it, which then will have the behavior graph of enemy behavior that has already been assigned. And there's a blackboard variable self, which is the instance of this current game object that this behavior agent is attached to, which in this case is the enemy. So as simple as that, I am just going to click on play, and then you will see that we will print hello world and very many times. This is because as soon as hello world is printed, the AI tree ends, and then since we have onStart set to repeat, it's going to repeat it every single frame after the execution has completed. So if we switch this off and click on play, you'll see that it only prints one hello world. And this is a behavior that you probably want to do for like one-use AIs. So we're just going to flip on repeat because it's much more common for an AI to keep on repeating behaviors that he has done before. So we'll just click this on. And now let's try to do something more advanced. Okay, we'll let our AI navigate to a point on the map. So if you followed through our thing last week, you should have already done the NavMesh baking. You should have already done the NavMesh baking. So to reiterate for those that haven't seen our video last week, to do the NavMesh baking, you just select the level parent, and then you add a NavMesh surface. Then you change the collect objects to current object hierarchy and click on bake. Then it will bake the NavMesh surface for you, and that is all you need to know. Once you've baked the NavMesh surface, you will see that there's this blue gizmos on top of your surfaces now, which signifies that the NavMesh has already been baked. Then you just need to attach the NavMesh agent, component to your enemy object in order to allow it to use NavMesh to navigate its movements. So we're going to log hello world, and then we're just going to add a new action. And as you can see, there's already a navigation subcategory that we can use. And then it lets us navigate to location, navigate to target, or patrol. We're going to start with navigate to location. So here, there is a shorthand for you to define sequences. Instead of needing to drag from one action to another, you can attach it directly, and then it will give you this very big block, which is going to execute from top to bottom the number of actions. So you don't need to drag a lot of arrows, and it looks much more compact. So here, you will see that it requires us to set an agent and then navigate to a vector tree of position. For this agent, we want to attach this enemy object, which in this case, it would just be self. So what you want to do is to go to Blackboard and then drag self in. And then you'll see that it says self navigates to a vector. What this is going to do is to make this enemy object navigate to the vector point of 0, 0, 0. So let us select the enemy, and then we can see that this is quite far away from 0, 0, 0. And 0, 0, 0 should be somewhere here. So, okay, maybe we'll try to move it around. And then let's change the position of it to be somewhere. Okay, negative 15, 0, 0 is okay. So let us change this here first to negative 15, 0, 0 in the behavior graph. And then as you click play, it's going to say hello world, and then it's going to navigate to this position. As you can see, it's moving, and then let us select our level parent. Let us select our enemy, and then you can see that it's trying to navigate to this position here, which is good. So now if we select this navigate, you will see that there are properties here that you can change. If you use this node, the speed on your NavMesh agent no longer matters. Okay, it's going to navigate on this speed. It's going to override the speed that you have defined on your NavMesh agent. So if we were to make this faster, for example, if we put this to 5, then it will move faster. As simple as that. If you don't have a NavMesh agent and a NavMesh bake, it will just move its transform so that it will just phase through the walls and then go directly to the point where it needs to go. Okay, so it says hello world and then it navigates to this part, and that's all good. What if now I want to make it so that every AI moves to a different location? Then we'll need to define a Blackboard variable that is not specific to the entire behavior, to all the behavior of this instance of the enemy behavior graph. So we just need to click on plus in the Blackboard, and I will be able to add new stuff. There's basic types like boolean, color, double, float, integer, and string. There's behavior subgraphs that we don't need to go through. Enumeration, you can create an enum type to be used. Events, list, there are different types of list. Resources, if you need to attach animations, audio, mixers, and everything, you can do that as well. And others, you can attach mono behavior to this. You can attach like all the mono behavior classes and all of this in Unity Engine, which is basically everything. Scriptable objects if you need to, but we won't be going into all those things. We're just going to add a new vector tree, and then we're just going to call this destination. So here you can switch on and off for exposed. If you click on exposed, it's going to expose it to the inspector window on the Unity editor. If you don't, then it's just going to be private. And then you will still be able to change the value through like code. You can randomize it if you have a custom node, but usually you would keep it exposed so that you can change the values in the editor directly. There's also this shared. This allows you to share the variable between instances of the same graph. Basically, it makes it sort of like a static variable so that it will be same, and you just need to define it once. But in this case, we don't need it. So I'm just going to do this, and then now you will be able to drag this destination into the vector tree component here. And then it will say self navigates to destination. So once you've done that, as you go back to the enemy class, to the enemy object, you'll see that this vector tree pops up in your Blackboard variable called destination. Now you can define a destination. So I'm going to define 1 to -1500 and enemy. We're going to duplicate it, and then we're going to do another one to a different position. And then let's move them away so that they're not colliding into each other on the first frame. Like this. So now I just need to click on play, and then you'll see that they will go to different locations on the map. Okay, they'll go through the stairs, and then one will go there, and then one will go here. Just as what we have expected. Good. So this is not all you need for behavior graphs. Okay, there are more to do. So we're going to explore some different things to this behavior graph. And let's try to make a very simple AI. We're going to make our enemy to patrol between 2 points, and then if the player gets into a specific range of it, it will pursue the player indefinitely. Okay, let's not make it too complex. So what we'll need to do, okay, now we can delete all of this. Okay, this is just to get you started with behavior graphs. We don't need this. So what we first need is to define that how we patrol and how we can move around. Right. So what we're going to do is here, we're going to create a flow. We're going to create a sequence. And let us just align it because I have OCD. So we have a sequence. So this should do two things. It should patrol, and then it should chase the enemy, chase the player if the player is too close. So let's do the patrol first. We're going to drag one down from sequence, and then we're just going to use the patrol node. So the patrol node lets you get an agent to patrol along waypoints. What is waypoints? Waypoints is a game object list. You can click on this link to see that what type of variable it is. So we know waypoints is a we know waypoints is a game object list. This means we're gonna need a list of game objects to act as waypoints. So what we're going to do is here. Okay, let me just delete this that I did for testing. We're gonna create an empty, and then we're just gonna call it waypoints, and then we're just gonna center it to 0, 0, 0. Then we need to create waypoints. Let's just do it for like 3 points on the map. So here we're going to create 3 empty objects, which will be waypoint 1, waypoint 2, and waypoint 3. Now we can assign them to different points in the map. So let's make this simple. We're going to assign waypoint 1 down here. We're going to assign waypoint 2 here. Okay. Somewhere here. Working on 3D is not very good. Okay, so somewhere here is fine. And then we'll do waypoint 3 Let's do it like here on this side of the map. Okay, it doesn't have to be very precise. We just need to get like some kind of indicator that it's working. Good. So we assign these 3 waypoints. As simple as that. Now we just need to make this a list. So you just need to define a new game object list in the blackboard. And then we're just going to call this waypoints. So this will be the waypoints that we're going to go on. And as you can see, the list is empty. So we're just going to go on to the enemy, the single enemy that we have. And then we're going to select this, and then we're going to drag in the 3 waypoints. So we're going to drag in waypoint 1, 2, and 3. Now we have the waypoints. Now you just need to assign this back onto the nodes, so it will say self patrols along waypoints. As simple as that. So now as I press play, you'll see that it will go around all 3 waypoints once. There's a problem. Now my AI is not moving. The reason is because in the patrol node, the speed is predefined to 0. We just need to increase it. So let's push it to something fast, like 5, for example. And I click on play. Now you will see that it will go between these 3 points. Oops. Did I save it? Okay, I think it should be saved. Let me just double check. Yep, so now as I press play, I should be able to see it going. Okay, that's weird. So now we don't know what's going on. What we're going to do is to click on debug. So now we enable debug, and then as we press on play, we can see what is going on with this thing. So it is running. Self patrols along waypoints. It has already set a navigation here, but it's just not moving. Okay, it's because the NavMesh agent speed is 0. This does mean that I probably did not change the speed. Okay, let's play again. I think this time it should work. Yes, okay. The save probably bugged just now. So as you can see, it moved to the first waypoint, waits for a second, goes to the second waypoint, waits for a second, and then move towards the third waypoint, waits for a second, and then it will go all the way back to the first one. So the patrol is sort of an infinite loop. Right. It will just keep on going the same waypoints over and over again, and it's not going to return a success or a failure status. And this is apparent because you can click on this and click on inspect script to see what is going on behind the scenes. So here, as it opens up Visual Studio, you will see that this, just close on random tabs, it will do status failure if the agent value is null, status failure if the waypoint's value is null, status failure if any of these is null again, so it's going to check this very many times, and nothing else. This means that this will never return the success or failure, and it will just keep on going indefinitely, which is sort of the behavior that we want, because obviously when you patrol along several points, you want it to keep on going. So then you would ask yourself, like, how can I sort of like preemptively stop this? There are several ways that you can do this, but we're just going to pick a very naive way today to implement this. So before we work on that, we need to have a way to detect if my player object is very close or is within proximity of the enemy, so that we know who we can chase. And unfortunately, there's nothing like a distance node that you can do. This means that we need some kind of behavior to check for this. And the way the thing that we can do with this is, okay, we will be able to define our own custom nodes for this behavior. So in this enemy, I'm going to create a new script. Okay, just be a simple mono behavior script, but we will have to change this. And let's just make this called detect player. Okay, very simple. So here in the detect player class, we will need to define it as a node. So we can just copy whatever is here for patrol action. Okay, there's these things that I'm just going to copy over. And then we're going to remove the ID field from the node description. So I'll go through what every single one of this means, right? So the name is the name of the node that you want it to appear in your behavior graph. So in this case, we're just going to call this detect player, because obviously this is going to be detect player. Okay, we're just going to call this detect player. You can put a space between it, it's okay. The description is the description you want to show up in the tooltip. In this case, move a game object along waypoints. If you check here and you click on it, it shows up here. So this is the tooltip. So you just want to define a very short and concise tooltip for other developers in your team to know what this node does. So in this case, we're just going to call this like detects if player is within a certain radius. Okay, I can't type. Good. Category is where you want to put this in your create node context menu. So this is an action, which obviously is an action. If you don't put, yeah, this is an action. So you put this in an action. And then I'm just going to give this in a category we call utility. So you can define subcategories on your own. Recall that utility is not actually a subcategory that is predefined. Then this is the very interesting part, the story. The story is what defines this line of text. Notice how you would be able to drag and drop in things. In the original case, it says agent patrols along waypoints. Agent patrols along waypoints. So if you were to put these things in these square brackets, it will open up the functionality for you to drag and drop Blackboard fields, Blackboard variables into your node. As simple as that. So we're just gonna say agent patrols, not patrols, agent detects enemy, or no, player. Agent detects player within radius units. Okay. So now we have agent, player, radius. We have three Blackboard variables. Okay, and here this is no longer going to be a mono behavior class. we need to change this to this action class. Okay. And it will say that action is an ambiguous reference between Unity behavior action and system.action, because there's also an action class in system. So here we're going to do some C# magic. We're going to define that using action is equals to unity.behavior.action. What this will do is to override all the action classes that we write in here to be Unity behavior action and not system action. We explicitly define this. Besides that, this also needs to be a partial class. This also needs to be a partial class. If this is not a partial class, this doesn't work. Now we just need to delete all of this. Okay, we don't need any of those code anymore. So let's start with defining the Blackboard variables. Okay. In order to define a Blackboard variable, you first need to make it a serialized reference. Where is my serialized reference? Okay, it's in the Unity engine namespace. Okay. And thank you, Visual Studio. So we need to first define a serialized reference, and then it's going to be a public Blackboard variable game object. So the Blackboard variable is a generic type, so you can just put it in the square brackets what type you want. And then note, you should always put this as the same name as you put in the story. If not, the toolkit doesn't know what field it should assign this Blackboard variable to. So again, we're going to do this the same for player, and then we're going to do this the same for radius. Okay, and then you can also define like a default value for it, just using this. So every time if you use this node now, as you drag in, it will always have a default value of 10 for radius. So now we are going to need to do a protected override status. Okay, status. And then we're going to do on start. So we will define the behaviors that we want when this node starts its first frame of execution. In this case, we're going to say that if any of this value is null, if the agent is null or the player is null, we're going to return the failure status. This means that we don't want to continue the execution of this node anymore because you haven't assigned a variable to it. If not, we'll return status dot running. Okay, this is as the same as what it's going to do. So we can look at how many kind of nodes that we have for our status, right? That's uninitialized. The node hasn't started yet. This is generally for internal use only. You don't want to return this as a method, as the value as you return from any kind of method. There's running, which indicates that the node is currently running. There's success, which indicates that the node has succeeded. Failure, which node has failed. Waiting, it waits for the current child nodes to complete. You only need this if you are defining your own sort of what do you call that? You only need it if you're defining your own control flow nodes. You don't need this for an action node. And there's also interrupted, which is if the node has been interrupted. Usually this is for internal use also. As you abort the node, it will always return an interrupted state. But we won't go through that. For now, you just need to know these three things. Running, success, failure. That's all you need to know for basic node programming. So, as we start, if the values are false, then we return that it fails. If not, then it will obviously it will continue running, so we will have to return it as running. If we return success here, then on the first frame, it will always just stop its execution after the first frame because it returns success. If a node returns success or failure, you always go to the next sequence. It's only when it is running that you will continue this running. So you're going to now override the method on update, which again we're going to do this check again. This is so that if in case in any point of execution the blackboard variable loses its reference, we will be able to return the status failure. Just like the patrol node, we always want to be able to check this indefinitely because we want to be able to know if the player is within proximity all the time. So the default return value for this would be status.running. So let us define the behavior that we want for this detect enemy. This detect player node. It's as simple as just checking the distance between agent and player. Is it like within radius, right? So we're just gonna do that. So if vector3.distance agent.value.transform.position to player.value.transform.position is lesser than or equals to radius.value, then we'll return status.success. So every single frame on update is going to check the distance between, and then if this is if the distance is now lesser or equals to the radius that we want to check for, then it will return a status of success. Once it returns success, the execution of this node stops. Correct? It will go back to the previous level of control, and then we'll hand over the control to see what is the next sequence we need to what is the next sequence of execution that we need to do for this behavior graph. Okay, that is simple enough. So now we can get back to here. Okay, we can get back to here, and then we can right click to add. And we're going to add a we're going to add this node. We're going to do utility detect player. Okay, so we have agent, we have player, we have units. We can now assign these to blackboard variables. We first need a reference to the player, then we need a reference to the unit. We need a reference to a radius maybe, so this is just going to be a float, and then we're just going to name this radius. So let us assign these into the blackboard. So, and then we just manually add a value. This means we are not assigning the default value onto it. That's all good, but if this runs all the time and in a sequence, we can only execute one action node at the same time. If the patrol nodes run all the time, then how am I supposed to execute the this detect player node? Question mark node? No, that doesn't solve the problem, because as soon as we reach the patrol, it's just gonna get stuck there. It's not going to go back. So here is extra node that we have not gone through in the behavior graph, that behavior graph example just now. It's the list of parallel nodes that you can do. Okay. In parallel execution, it says run in parallel, wait for all, or wait for any. But these are not actually what we want. Unfortunately, this package is still sort of incomplete. So there are several things that don't show up properly. But if you do it like this, it shows you these branching options that has something that we need, which is run in parallel until any succeeds. If you try to find this, okay, if you try to find this, you can only find run in parallel, but you will be able to change this like this. This is an extra step, but we can do this as well. So you just drag back the sequence that we lost, we deleted. Then we go to run in parallel. So in parallel, we're going to run these two things. It says in parallel, but actually, if we inspect the script, this is not parallel. What it does is that on every update, it executes this from left to right. But it does it for every child object. Instead of being able to execute only one action at the same time, this run in parallel node forces you to execute for all the sub nodes, the subgraphs of this, all the children of this node. So it still goes left to right, but now we can execute multiple actions at the same time. At the same time, as in the same update tick, but there's still a strong sequence between. So here we're just going to change the parallel node to until any succeeds. Because, you know, as the detect player node succeeds, it will then return it back to one level of execution with respect to this sequence node. So now we will be able to add the logic for us to chase the player. In this case, it's just going to be navigate to target. Navigate to target will always navigate to the game objects, the target game objects position. You don't need to update it every frame. It will only stop once it reaches the position, which we'll show you later. So here, again, we just drag these things in. Self navigates to player. As simple as that. Right. So, again, this doesn't look very aligned. I'm just going to right click on this and then align it again. All children. Okay, now this looks much better. Good. So, let us assign these back. Then let us align this again. Now, it's going to patrol along the waypoint, and it's going to, at the same time, check if the player is within the radius. If it is, then this node returns success. It goes back one level, goes to the sequence where it's going to do this, self-navigates to player. Good. So to see that this is working, we're once again going to just go back here, go to enemy, and making sure that we have assigned the proper values to our stuff. So player, just gonna assign player to this. Making sure that player runs faster. 510 is good. Making sure that this navigate to a target has the proper speed, which in this case it should be 5. Okay. And then all we need to do here, okay, is again to click on debug, make sure that this is debugging. Okay, this is already debugging, and let's click on play. Can I not shrink this window more? Apparently not. Thank you, Unity. Okay, let's just dock this here. Okay, much better. Okay, so now we are going to click on play, and then you'll see that what this is going to do is that this will patrol around, and since the player is so far away, it's not going to detect us yet. And then you see that these two nodes are currently running. This node is waiting for the execution of the child nodes. Now I'm just gonna move towards the enemy. Now it switches over here because these have all returned success, and this one has returned interrupted because, you know, it stopped. Now as I'm getting pushed away, you see that the graph glitches out, but that's intended. So it will navigate to me. As it reaches me, okay, as it reaches me, this node returns success and it goes back up. It's supposed to end, but because on start we click on repeat, so it's going to start from the left again, where it's going to check. This is going to execute for 1 frame, and then detects that the player is within range, and then it's going to go back down to here. So you see that it sort of glitch out. But this is the intended behavior. If we were to flip this off, no, I think we can't flip it out during runtime. Okay, if we were to flip this off and we try to run this again, you see that as soon as it stops next to me, it's going to stop the execution of the thing. It doesn't. It's interesting. Okay, it might have something to do with how this is working. So let's just inspect the script. Status failure, status failure, status success is navigation complete. I think it's because of the braking distance. It might be. Okay, let's increase the distance threshold. Is it really important? Not really. But okay, yes. Now it stops. The reason why it doesn't stop just now is because the distance is too far away. The distance is too short. It never really get to brake properly. It just hits into me and it just keeps on trying to move around with me as it pushes me away. But yeah, that is not very important. But yeah, now you can see what these parameters actually mean. So that is pretty much it. You need to know about a behavior graph. The different kinds of execution, the different kinds of how you can make your custom nodes, how you can try to create different behaviors with it. Blackboarding, things like that. There are more stuff to behavior graphs. You can define things like custom events that will trigger, and then you can listen in onto those events, but I won't be going through that today. It's quite an advanced topic in my opinion. You need to know how events actually work. That would be a completely different rabbit hole that I am not intending to cover today. So, any questions?
For the sequence, like before we added the run in parallel or the until it succeeds part, could you swap them instead? So like you detect the player first and then you patrol the point?
This and this?
Yeah.
So if I were to swap this, for example, if I do this, right? Okay, if I just do this, is this what you mean?
Yeah, kind of, yeah.
Okay, so
It won't work, but I'm curious as to why.
okay, so let us debug, right? And then we're just gonna see what's gonna happen. It will never patrol. Because remember here, what we do in the detect player is we always return status running until this. So it always runs. And the sequence node will, as we inspect the script, the sequence node is going to check if child.status is success, then it changes this to be success. It changed this to be running so that it can go to the next node. If my current node is running, then I'm going to go to a different node. We're gonna increase the child count, so we're gonna traverse next to the next node in the subgraph, and then if it's failure, then we return that this is failure, so it propagates upwards. If not, if my child is currently running, which is not here, then I'll just keep on waiting. I'll wait until a child is either success, which I move to the next sequence, or fail, which I propagate upwards. This is what this node does. And it's the same if you try to do it this way. So if I remove this and then if I put this down, implicitly what this does is it just creates a sequence between these two. So it will look something like this. So another sequence. Let's remove this. Okay, it will look something like this, but it's just a shorthand of that, and this would be an execution like this. And then if you were to run this, you will see that the same behavior happens. It will just get stuck on the tag radius unit. This is waiting, this is running, and it never goes into here. If we go into range, okay, then it will start patrolling. Obviously, this is not the behavior that we want. So there are better ways to do this. For example, defining an event and firing that event in your detect layer node, and then you execute this new subgraph as the event is fired. But I'm not going to go into that today. Okay, questions? Other questions? No questions? No questions? Then we are good. So that is all. There are more documentations you can read up. This is the behavior graph. This is the behavior graph documentation page. It tells you basically all that you need to know, all the basic stuff, and then all you need to do is to extend on this and try to work on more complex behaviors. It tells you how you can write scripts with this, interact with behavior graphs in C# scripts, how you can use other scripts to change the behavior graphs here, how you can create a behavior graph with generative AI. As you probably know, Unity has their own large language model called Muse. It does require a subscription, which unfortunately I don't have. So you can use Muse AI to create a behavior graph for you. I don't know if it does custom nodes, obviously because I can't test, but I believe it does. So this will significantly reduce the time you need to create workflows. That is assuming the AI actually does work. I am quite skeptical on that. But yeah, you can create these kinds of nodes. You can create action nodes with generative AI. Yeah, it does create custom nodes. So that is quite interesting. You can, it tells you how to use event nodes. So you'll be able to do like different types of subgraphs that runs in different actions, runs when the event is triggered, and things like that. This is one of the readings that I would recommend reading up if you want to go further into behavior graphs, because events are quite useful. Okay. And using conditions, which I didn't go through today. The condition node is a little bit wonky here actually, because instead of returning back, it propagates down. So it's a bit weird in the implementation of it, but it kind of serves its purpose well, so I guess I'm not complaining. Yeah. Yeah, that's about it. Save and load running state. You can actually save the states of your AI. It will get serialized, and if you have some kind of like a save file serializer that you do in your game, you can save the behavior of AI states into your save file as well, so that as you load back into the game after you exit, the AI is going to pick up where it last left off, and then it will continue. It will continue where it last left off, which is probably good for single-player open world games like AAA production where your AI is not just going to randomly reset its aggro as you log out. It's one of the major glitches in games like 10 years ago. Nowadays, it's very difficult for you to find an example like this. As you load back in, the AI state is going to load from where it last left off, and then it will stay in the aggro state. Some games still maintain the behavior of not saving the state, so it's easier for you to exploit. If you're in an unfavorable boss match, you just quit. You log back in, and then it will just reset its aggro, and you can run away. With behavior graph, Unity's behavior graph, you can save the state, but it would be quite difficult to do. This documentation tells you how you can do it. Yeah, you just need to read this up. It tells you everything you need to know. Troubleshooting issues, like it tells you how you can troubleshoot, how you can debug. We have gone through debugging, so you don't need to know this anymore. It's as simple as turning on debug. That's it. So yes, that is the readings. Any other questions? If not, then this will be it for today. And I guess for the rest of the time, you can try to play around with it and see what kind of complexity you can come up with for the rest of the hour or so. So yeah, thanks for coming. And it will be recess week next week, so we'll have no session. Since it's going to be the midterms week after recess week, we'll have no session on week 7 as well. Once we come back, we'll go through a different topic, which is not going to be game AI this time. We'll do software engineering principles in games, which I think would be a much more interesting topic for those that are aiming to be game programmers. So yeah, I hope to see you guys on the week of the week after. The week after the week. Okay, whatever. I hope to see you guys on week 8. Okay, it will be the same room, same time, and we'll go through different topics. There will be 2 weeks in the software engineering practices. We're not only going to be going through the software engineering principles. We're going to go through some tools that Unity provides you to do things like testing, debugging, profiling, and things of how you can actually try to do software engineering in the Unity engine itself, which I think would be quite beneficial. So yeah, so if there's nothing else, I hope to see you guys on week 8, and thanks for coming. Stop.